So, if you haven't upgraded your PyTorch to the latest version, you might be missing out on a really cool feature. If you have, you might be underestimating the power of the new PyTorch version. Stick with me in this video and find out more. So this new feature I'm talking about directly affects how the transformer models work, particularly the computation of the self-attention layer. In the PyTorch backend, you have something called the scale.product attention, which uses the SDP kernel or the scale.product kernel to do the computation. Once you go to the PyTorch documentation, you can read about how this self-attention computation works. There are a few different options that PyTorch lists down in this documentation. You have a native implementation of the self-attention layer, which is in C++. You also have a memory-efficient implementation of the self-attention layer. Finally, you have something called flash attention. Further down below in the documentation, you can see how you can enable or disable one of these options. In this video, what we're going to look at is how much of a difference it makes by enabling or disabling the flash attention. Flash attention is a recent paper that came out which almost revolutionizes how the attention computation works. All the computations we had so far uses memory quadratic of the sequence length. However, the flash attention computes this with linear memory limits. You can read more about how flash attention works in the paper link below. Great, now let's dive into the code. So here I have my Google Colab runtime. A really important thing you must do is change your environment so you have access to a GPU. Even with a free account, you can get access to GPUs in Google Colab. You would be getting a NVIDIA T4 GPU with 15 GB memory. It will become clear why this is a requirement as we go through the video. Once you install the libraries, let's check our PyTorch version. Here, we have version 2. The earliest version which I have seen flash attention enabled is version 1.13. So you would need at least that version in order to run this code. What I'm going to do in this exercise is load a text file and then run that through a transformer model and look at the time it takes to infer and the memory consumption. We will do two experiments, one without flash attention and one with flash attention. Talking about the data, it's a plain text file. You have a bunch of text present in the file. This text was borrowed from a story. Now let's talk about the hyperparameters. We have the batch size, which is 32. We have the number of layers in our transformer model, which is 6. Then we have the dimensionality of the hidden layers, which is set to 512. And finally, we have the number of heads in our self-attention, which is set to 32. Finally, we have a range of sequence lengths in order to test the memory consumption as we increase the sequence length. Setting up the transformer model in PyTorch is pretty easy. You just define a bunch of transformer encoder layers and with that, you build the transformer encoder model. What I'm trying to do here is build a transformer decoder-like model. The reason I'm using the encoder layers is because the actual implementation of the transformer decoder layer that has a required argument where I need to provide the last output of my encoder model. But here I need a plain transformer decoder model. The way I do that is use the encoder layers and set the isCausal parameter when I'm calling the model to true. That way I get the decoder-like self-attention computation. Another important distinction is setting the batch first to true. By default, PyTorch uses the format of sequence length, batch size, and then the hidden dimensionality, which I don't personally like. I like to think of input tensors as batch size, then sequence length, and then the hidden dimensionality. So I'm setting this batch first to true so that I get my tensors the way I like them. We also set the D type to float 16, and I will explain why as we get to the flash attention experimentation. Then we define a few utility functions. First, we have the get GPU utilization. This function gives you the exact memory consumption of your GPU at a given time step. This is quite important for us to get the memory consumption with different sequence lengths as we input data into our transformer model. Then we have the run single iteration function, which takes the model, generates some random data, and passes that data through the transformer model we defined. Finally, it outputs the time it took to do the inference and the memory consumption. The final function is simply creating a data frame with those time and memory results. The first experiment we are going to do is without flash attention. In these newer versions, flash attention is turned on by default, so we need to manually switch it off. How do we do that? We use the SDP kernel context manager. If you run your model inference within this context manager, you can control what specific computation of self-attention is used. Here you can see I'm disabling flash attention, but I'm enabling both of the other ones. So this gives a fair comparison. How much contribution does the flash attention make compared to all the other optimizations we have? There's a few things to note here. First, we're going to do a dry run so that our GPU is warmed up. Otherwise, as the first iteration, you might get some false readings because the GPU might take some time to warm up and run through the computation. So this computation that's happening outside the loop is for that. Next, we use the CUDA.synchronize function to synchronize our operations. CUDA launches kernels asynchronously. So if you don't synchronize at each iteration, again, you might get some false readings around the time it takes. We're going to be running our model on a sequence of 256, 512, and 1024. We'll store the time and memory results into a Parquet file. Before we run flash attention, there's a really important thing you need to do. You have to restart your runtime. This is because you need to release the GPU memory reading. Otherwise, you're going to get false readings when you run the flash attention because flash attention takes way less memory than the original attention. When running the transformer model with flash attention, everything is similar except for one, the SDP kernel context manager. Here, we are enabling flash and disabling both other options. So the only thing that is happening here is the flash attention. We run the code and we get a similar time and memory profile. Alright, remember I said that we're using the D-type float 16? Here's why. Flash attention works on the GPU. It is a way to optimize for the memory hierarchy that is in the GPU. And the current implementation of flash attention only supports float 16. So to make sure that all our data types play nicely with each other, we're setting our model to float 16. Secondly, you need to be careful on which GPU you're running this code because some of the older GPUs may not support flash attention. Next, there are various restrictions on the head dimensions you can use. You can find all the information about all these restrictions in the flash attention GitHub repo. I have provided you a link in case you are interested. Also, some of these limitations are noted in this notebook. You will find the link to the notebook here as well. With that away, let's run with flash attention. That's pretty impressive. With flash attention, the memory consumption is way less. Let's store the results into a Parquet file so we can load it and analyze it later. So here, we're going to set up our data frame so we can create a few bar charts for time and memory. Initially, for time, you can see that there is a small speed up with flash attention. Remember that you will get a better speed up on newer GPUs. This is because how the flash attention works. The more on-chip memory your GPU has, the better the performance of the flash attention computation will be. The real interesting graph I want to bring to your attention is this second graph, which shows the memory consumption. You can clearly see the exponential trend of the native self-attention computation versus the linear trend of the flash attention computation. So I didn't run for larger sequence lengths because I can't compare the large sequence lengths to the normal attention computation because it just goes out of memory. But with this exact specification, you can actually fit a sequence of, get this, 12,500 elements long. Or if you only take a single data point, you can fit a 400,000 items long sequence. That's about a 600-page book. So, as I said, if you haven't upgraded your PyTorch version, you should definitely do that because flash attention is enabled by default. So you're getting all the benefits out of the box. If you already did have PyTorch version 2, so you might have been restricted to shorter sequences because you didn't know about it. So definitely try out longer sequences and you'll be impressed. That's the end of the video. If you enjoyed this video and if you want to learn more about machine learning concepts and really cool novel technologies, subscribe to my channel, Deep Learning Hero. I will see you soon with another video.